Once you know a series, you can actually use that series to find other series. So different things you can do with the Maclaurin or Taylor series is you can substitute into it. So we're going to show an example of that. You can multiply or divide your series by a constant or a variable. You can add or subtract two series, and then a little later we're going to show you that you can I'm going to show you that you can take the derivative or integral of a series. Or you might be recognizing it as the sum of a geometric series, which makes things a little bit nicer. So the first thing we're going to do is actually substitute into a series. So that might be some scenario where you're given f of x equals sine of x squared, and you need to know what the infinite series is for this function. Well, I don't have one for x squared without doing a lot of work, or sine of x squared, but we already know what sine of x is. So I know that sine of x is equal to, and again, sine is an odd function, so odd powers, x to the first, then x to the third over 3 factorial, then we'll have an x to the fifth over 5 factorial, an x to the seventh over 7 factorial, and then sine is alternating, so positive, negative, plus our ellipses, and then we have, it's the sum from n equals 0 to infinity. We'll have a negative 1 to the n, and then we have x to the 2n plus 1 over 2n plus 1 factorial. Well, if I want sine of x squared, what I'm going to do is substitute this x squared in for every x. So I'm going to do that in a couple of steps. So sine of x squared will be x squared minus x squared to the third over 3 factorial plus x squared to the fifth over 5 factorial minus x squared to the seventh over 7 factorial plus, I forgot my equal sign up there, and this equals the sum from n equals 0 to infinity, negative 1 to the n, that hasn't changed. My factorial hasn't changed, so 2n plus 1 factorial. But instead of an x, I'm going to substitute in my x squared to the 2n plus 1. So if I wanted to simplify this, I would know that sine of x squared is equal to x squared minus x to the sixth, with a power raised to a power, over 3 factorial, plus x to the 10th over 5 factorial, minus x to the 14th over 7 factorial, plus our ellipses, equals the sum from n equals 0 to infinity, negative 1 to the n, and then this will be x to the 4n plus 2. I'm multiplying my exponents together over 2n plus 1 factorial. Either one of these versions is correct.